Hopefully it will work, but welcome to ECE 320A.
Are your microphones on?
My microphones are on. Are you not hearing through the room mic? You're not hearing anything from the room mic? You are? We adjusted the gain a few days ago. Hopefully it's somewhat working, but I don't want to be shouting. And you can still hear me in the back? Okay. So I will assume that you can hear me. You can, I hope, because of the distance. But I think the speakers are filling in the gaps. But the speakers may just be here, and it's moving to the back. Yeah, it's going over. This whole lecture may go over my head, but we'll see what happens. The sound, I hope you can have, okay? I typically start off by giving, as you're walking in, this screen that may not have all of the goals that we want to accomplish, but the announcements that you are responsible for knowing will be there hopefully a few minutes before class begins. There are attendance sheets going around. The passport assignment, that's something that is due by the 20th of January, and that you will submit into the assignment Dropbox that's labeled passport assignment. And we'll talk a little bit about that. That will be on our goals, but these are telling you what you need to be responsible for in this class. The other is you need to make sure that you have access to Mastering Engineering, and that's available through D2L, and we'll talk a little bit about that as well. Here are the goals for today, and see, I can't even still get them on one screen, but we have preliminaries, the introduction. Oh, I'm Hal Tharp, the instructor for this class as of today, and I will get to know you by your passports. That's how you get into the class, so that I understand who I'm looking at or appreciate who I'm looking at. These videos or these lectures will be recorded, both the handwritten, that will be in notes, and the audio with the video capture, and that will be available through D2L. Attendance is going around, as I said, and now what I want to do for today is the following. We want to discuss the passport assignment and talk a little bit about the syllabus for the class. And the syllabus includes information about gaining access to mastering, and I'll try to show you that where that is on the D2L website. It's really the course homepage on D2L. We will begin the semester with a quiz, since I know that you love quizzes, and then we'll, after the quiz or as a result of the quiz, we'll start walking through the overview of the class. How do we see this class in terms of content, topic-wise? What are we going to begin with, and where will we end the semester? And I'll try to give you a 30,000-foot view of the class. Essentially, it's the second half of the textbook that you used for 220 in terms of topics. That's the idea. So now what I want to do is discuss the passport and the syllabus. Maybe before I do that, we'll talk about here's what it might look like as a student. Here I'm pretending to be a student on D2L, and this is the course homepage. How many of you have already found this link in the lower right-hand corner of the course homepage? You can then click on that link, and that will take you into the Mastering website to access or put in your information to gain access to Mastering, and you need that to do your homework. So you'll need access to Mastering in order to be able to perform or do the homework assignments. Most of the material will be available if you click on the content page. And right now there's not a lot in there. You can see the outline on the left side. I've just put in Unit 1. That's now the single phase power. That's Chapter 10. There is information on preliminaries, and supposedly I've done some of that since there's a check mark there, since I'm a student pretending to be. Course business is where you will find a brief description of the class, the syllabus, etc. And then for your assignments, which most of those will be homework assignments within Mastering, you'll just submit your answers there. But for the passport assignment, you can click on that link and upload your passport into that Dropbox. The passport itself is here. Has anyone filled it out yet or completed it? A few. I would like to know your name, and then if you go by something that's not really or let's say your given name is Jonathan and you like to be called John, then that would be your nickname. If you're John Smith and you like to be called Bill, then tell me your nickname is Bill. Sometimes there's not a direct connection from me to know that that's what you like to be referred to. What you like, and it, I guess, needs to be PG rated, your nickname, since we're recording this. So don't get too creative with your nickname. It needs to be something that you're used to being referred to. Photograph should be up to date. Doesn't need to be your baby picture. I won't be able to do the age progression as well as some of these machine learning strategies can now. So give me an up-to-date picture, and then to give me something besides a face and a name, what hobby do you like? Typically it's easier for me to actually see a face and I think of their hobby than your name, in fact, but maybe I can get all of those connected. The other part of your passport is to read through 20 different rules. 10 rules concern good study habits, and another 10 refer to bad study habits. I would like for you to read those and actually then comment on one of those saying, oh, I really like this study rule as a good one, and I'm going to try to say whatever you want to say on A. B is, do some of these bad study rules, have you actually used those? Do they, or you've never used them, etc. But comment on a good rule and a bad rule after reading the 20 different rules. And if you submit that passport into the Dropbox, that's effectively your signature. You don't have to worry about signing in blood or anything like that. Submitting this into the Dropbox will be constituting the connection or the verification that in fact you have read the syllabus, which we will discuss next, and you've completed the passport. Questions on the passport? Yes. No, I would prefer most things that get submitted a PDF file. That seems to open up more effectively. I think I've provided in D2L you a Word document and a PDF. If you want to edit the Word document and then convert it to a PDF and submit that, that usually is more universally or easier for me to access than a Word file or some other Word form or document format. Other questions on the passport? Let's then talk about the syllabus. I have told you my name, and there's luckily only one number for this particular class, but I do have office hours 4 days a week, Monday, Tuesday, Wednesday, and Thursday. And they're at different times in case those times don't quite work with your schedule. Hopefully one of these will work with your schedule. If we can't seem to meet, obviously you can talk to me after class or via email and we can try to make a connection that way. The first page really talks about being successful in the class, and one fairly new book is Teach Yourself How to Learn, and that's available to you through the U of A book or library, and you can get the ebook that way or access the ebook that way, and it's really complementary to those study rules that I have you read in the passport. But if you're interested in trying to figure out how can I more effectively focus my time when I'm studying, what do I need to do? How many know the word metacognition? Not very many, and they do talk about that in the book to try to make you aware of how you learn and what's going on in your own head And that's hopefully going to improve your performance in the classes that you're working on. How many have heard of Bloom's taxonomy? So you can refer to that particular book and it will start coaching you through how to improve your learning in various classes. You'll need to spend a fair amount of time. You've probably heard a 3-unit class is about 10 hours a week. So you have 15 units of classes, 5 classes. That's 50 hours a week that you're supposed to be investing in your education. That's why education is a full-time job, even though you're sitting in class not that much relative, and this is beyond the time that you're in the class or in the labs. This is some of the main required material, but the book is the 11th edition of Mastering. And here is probably what you're more interested in. The homework is 10% of your grade. There are 3 exams. Those dates, I thought you would enjoy an exam on Valentine's Day, of course. We're engineers, right? What's the 14th of February? So we have an exam on that day. You'll love it. And then we have 2 more exams, and our final is not on a Tuesday or a Thursday. If you're used to always being on campus Tuesdays and Thursdays, make sure by May 8th that you have it blocked in that you can be here for the final exam, which is at 3:30 on that Wednesday. Here, as I said, is basically the second half of the textbook relative to these course outcomes. Do I have more? Here is that maybe more directly connected with the textbook. We'll be starting in chapter 10, and then we'll proceed on down through the end of the textbook. Was there a question? Yes.
Are you particularly concerned about students using the 10th edition?
So I'm not particularly concerned with students using the 10th edition. If you have a physical copy of the 10th edition, that's great. But when you're working the homework, I thought the publisher convinced me that I needed to be using the 11th edition. We uploaded what I wanted to do, and there are problems from the 10th edition, so it's kind of a mess. But if you're starting to do the homeworks, make sure you're doing those based on what's in Mastering. So if I say do problem 10.1, it may not be 10.1 in the 10th edition. That's probably not the 10.1 in the 11th edition, although that's what I was promised. So make sure that whatever you see in the Mastering, that's what you need to be working. Is that confusing? Probably. But just stick to the problem that's in Mastering. You can probably find something similar in the 11th or the 10th edition, but I don't know where they sit until I try to go through. In homework number 1, I tried to make the correlation. Here's the problem 10.1, and that's actually from the 10th edition, and that corresponds to this problem in the 11th edition. The publishers, what are we going to do? Always continuing to evolve the textbooks. So it's now into its 11th edition. But no, the 10th edition and the 11th edition probably aren't that much different. It probably is in the problem sets or the problems themselves. There's maybe different problems between the 2 editions. So just make sure that you're working the homework not necessarily based on what I say, but what is in the Mastering homework site. Other questions on the syllabus? So we're going to get through chapter 18, hopefully in the textbook, based on this outline. That means that we're ready for our quiz. Now I actually do want you to pull out a piece of paper and start trying to solve this problem. The problem is I'm giving you an input voltage applied to this circuit. The circuit has 2 resistors and 2 inductors, and I want you to find the equation for the output voltage that's measured across that series combination of capital R sub L and capital L sub capital L. And I'm hoping the screen is visible. Pardon? You may use your calculator if you would like to use your calculator. Apparently, if you're pulling out a calculator, you feel like you know how to start, or you feel comfortable with where to start, but are some of you still struggling on where to start or how to get started? I assumed you worked these problems all over the break between semesters, that you were just working chapter 9 all the time, and that's, I think, where this could be viewed as, although now I'm labeling it as a transmission line and a load more consistent with chapter 10. But what if you don't know where to start? How do you start or thinking about this problem? Let's say that you're in an interview and somebody puts this down in front of you and they say, what do you expect to see at V sub L of t? how would you maybe start thinking through that problem if somebody now said, oh, I want you to tell me what does V sub L of t look like in this circuit?
I expect to be less than voltage input.
So you would expect it to be less than the voltage input. Okay. So can we, how much less, or what would it maybe look like? There are some ways. How could we start to get a feel for this? In an interview, you might just sort of show your hands, meaning show your strategy to the interviewer and say, let me sort of think about this in a general sense so that I get a feel for what I might be expecting for V sub L of t. And one way that you might do that is say, oh, these inductors, they always kind of make things a little bit more difficult. What if I just neglected those inductors? Would that help? So can you simplify the problem? So now in terms of where do I start, one thing might be, can I actually simplify the problem? And if I do that by neglecting the inductors, then what do we have? Well, now we have something that looks like that, right? If we now neglect the inductors, if we short those out, if they're not present, now we have this is 2, and this, I believe, was 78, and this is now our V sub f of t, and we're now really sort of looking at a modified, maybe I'll make that a hat, put a party hat on, V sub L of t. This is not the actual V sub L, but now do you feel like you have a better understanding of what V sub L hat looks like and how to maybe solve that? Voltage divider. Now we're back in 220, aren't we? And especially if V sub S of t was some constant, but it's a sinusoid. If it's a sinusoid, what's V sub L hat going to look like? Sinusoid. We're not changing the shape. This is now just a direct division, voltage divider of V sub S down to V sub L hat. So that if we wanted to solve this, now you're saying, oh, we have a voltage divider that we can apply. And maybe somebody's going, oh, I forgot voltage divider. I don't even see that. Well, maybe you don't, but you probably can analyze this circuit by finding the current. Let's say that you now call this I sub, do we want to hat that? We could, since that's not really the current that we would want, but in this circuit it's just the current. Now we can find that current, and once we have the current, we know Ohm's law to obtain V sub L hat. That's just this R sub capital L times I of t. So we don't have to remember voltage divider. Maybe we forget voltage divider, but you know how to fall back on KVL and finding the current in this circuit. And once we do that, we have a little bit of a feel for what V sub L of t is going to look like. In this case, we said, oh, we have a voltage divider, or we could find this I hat of t. And once we have that, then this V sub L of t is now just R sub L I hat of t, where in fact this I hat of t was simply the applied voltage divided by the total impedance, or resistance in this case. We'll be dealing with the generalization of resistance in this class as impedances, and that's what I'll probably be using is impedance, so that we can have R's and L's and C's combined, but in this case it's just resistance, so that now we have R sub L plus R sub L. Well, where the first R sub L, you knew that that was lowercase, and the second one, being a little bit facetious, you probably couldn't tell by my voice that that L was lowercase and this L was capitalized unless I explicitly said that. But I wrote it down as R sub lowercase l plus R sub capital L. And in this case, what does that really mean? Well, if we now did that, V sub L of t is now R sub L over R sub little l, and there's our voltage divider that if we didn't remember, we now have it in front of us. And in this case, R sub capital L was 78, and little r, or R sub little l was 2, so we now have a fraction, and it's a big fraction of what we started with. It's less though, isn't it? We now have 78 over 80, and now if you wanted to start sketching this for the interviewer, you can start sketching this. You can say, oh, then if V, that looks like a pure sine wave to me, that's now, again, you'll have to do better with your hand sketches than I do, but I can label it. This is now V sub s of t. And that means then that the other one is probably indistinguishable at this scale, but I'll exaggerate it a little bit. And now we have, oh gosh, it's supposed to look exactly the same, but this is now do you have a feel for what V sub L of t looks like? And you know what V sub s of t was. That was a sine wave of 60 hertz, or in radians, it's 2 pi 60. So that one, 60 hertz, is what's coming out of the wall. We'll be using that a lot. That's coming out of the wall in the United States. If you go to Europe, it might be 50 hertz, or somewhere else it might be different. But here we'll probably use F as 60 when we're talking about power problems. 60 times 2 pi, if we rounded pi to 3, that's 6 times 60, 360. You add in a few more digits for pi and you get 377. So if you see an omega of 377, you now know we're talking about something coming out of the wall, or something power-wise in the United States, if you see an omega equal to 377 radians per second. Okay. What have we just said? We had an omega equal to 2 pi f and that now allows us to think about what this is going to look like. But in this case now that we put those inductors back in, what's going to happen? Or if we put those back in, I'm assuming that you ended up 220 with sinusoidal steady state analysis. Is that true? That was chapter 9. And really that's what one way that you could have started analyzing this original circuit. But in a general sense, now that you have sort of reminded yourself where we're playing, oh, if I eliminated the inductors, I now know what V sub L looks like. If I put those inductors back in, how's that going to change V sub L? Is the frequency going to change? Is F going to change? Is V sub L going to be at the same frequency as V sub S? Why? If you can't hear, I'll repeat the answer. The answer was V sub L was the same as V sub S. Why do we know that? We have a linear system. We have fixed, and it's time invariant. So time invariant means these R's and L's are not changing with time, and we don't have any nonlinearities in those values if we operate within a well-defined domain. Obviously, if you really stressed this system, those resistors might have some nonlinear characteristics. But in this particular class, we're assuming that we know Ohm's law and its generalization for capacitors and inductors are V is equal to Ri or V is equal to Zi. We're living with that. If it's a linear system, then we put in a sine wave of some frequency. That's what I'm meaning when I shake. Then you come over here and you're seeing that same frequency anywhere else in the circuit. You're not going to see 10 hertz anywhere in that circuit. Everything's going to be 60, isn't it? And this is not 60. It's definitely not 60 times a second, is it? No. That you might not even see that one if you started going at 60 times a second. I need to do that when I get home. You know, my Fitbit might really go crazy. Not that I have one of those, but this is now what we have, right? So we now have a better feel, a better understanding of what's happening or what's going on if somebody says find V sub L of t. We know that V sub L is probably, it could be actually, because we have some energy storage devices, it could actually amplify. It could be bigger than V sub S if we're in sort of a resonant condition. But here, if we just had pure resistors, it's going to be less because of the voltage divider. And we know that V sub L is shaking at the same frequency that we injected. If we change this F from 60 to 10, then everywhere in the circuit, you're going to see 10 hertz. When you first energize this circuit, you might have some transients, but in steady state, then everything's working at 10 hertz. Now, do those inductors make any other difference? Does V sub L of t, not V sub L hat, but does V sub L of t, we said it's the same frequency. Is it, now it's what? The phase has changed. Oh yeah, the phase of the moon. I've got a full moon, I've got a half. Phase, what's phase? Well, phase in this case, in our circuits, really just means there's a time variation between the peaks and the valleys, or the zero crossings of this blue curve and the black curve. So really, it could be just a shifted version of what we've drawn here because of that phase shift, but it's going to be the same 60 hertz. It's just going to be offset. It's going to have a phase difference. It's going to be offset in time. And now you could sketch that for your interviewer. You could say, this is what V sub L looks like. Do you really want me to go through the analysis? You might not be quite like that. But you might suggest that you know what's expected, and now you can start thinking, okay, if we're doing sinusoidal steady state analysis, what's the next step in that process? If the interviewer says, okay, smarty pants, you told me what V sub L is, can you now calculate it, do the analysis? What did you do in chapter 9 in sinusoidal steady state? Why did you start bringing out your calculators? We're looking for impedances, aren't we? Or we're looking at analyzing this using concepts connected to phasors, complex numbers, magnitudes and angles. There's our angle is a phase, right? So now if we have phasors, what's the impedance of the inductor at the load? That's the capital L now, Z sub L. How do I find the load impedance associated with that inductor? That's J omega L sub L, right? So this is now J omega L sub L. So that now we have J, and omega we just said is 377, and L was some silly millihenry value. And that actually ends up being 59. Did anybody get that on your calculator? Was that a yes? Good. So now we know that Z sub L is J59. And we can find the other impedance of the inductor, Z sub lowercase l. That was now 2.653 times 10 to the minus 3 for millihenries. And that ends up being J1. Pardon?
I'm like, really?
Really? So that's what you were punching and finding on your calculator. When you, I hope, did anyone get a 1? Good. So now we know that V sub S of t is 311.1 cosine of 377t. What if we put that into a phasor? What would the phasor look like if I now say, oh, I want to work all of these with complex numbers. What's this phasor representation for little v sub s of t? It's a magnitude and an angle. And we have that now given to us. This is now 311.1. What's the phase? 0. Now in this class, it's going to be critical, and this is where you might get tripped up, to make sure that you know what that value for your magnitude on your phasor represents. Is it actually the maximum value in my sinusoidal function, or is it an RMS value? We will probably prefer to work with RMS values because we're going to be dealing with powers, and it makes the equations a little cleaner to work with RMS units. But in this case, that particular magnitude is, let's say, V max. And that's now the maximum or the peak value of our sinusoidal source voltage that was given to us. And if we do all of the calculations in terms of maximum values, then you know immediately when you get your answer that you can plug that in as your maximum value in a cosine expression for little v sub L of t. If we now don't want to be working with max values and we wanted this in RMS, did you do that in chapter 9? A little bit. So now we can show that the RMS, the root mean square for cosines, is related by this factor of square root of 2. So if we wanted our phasor to be in terms of RMS units, we would just take this maximum value, divide it by the square root of 2. We haven't changed the phase. And if we do that for these numbers that I've selected, now we have 220 for our input sinusoid in phasor form. This is now volts RMS. And we now have our circuit again, that interviewer just won't go away, but we've now boiled this down to that's a 2, this is a J1, this was 78, and this was J59. Here is our V sub S RMS, 220 at 0 degrees. And now we just want to find this complex number, capital V sub capital L bar. And we can do that now with complex algebra. We can do what we just did. We could find Well, if somebody now says, oh, if I knew this, and you might even say that in your interview, you might say, well, if I assume I can calculate I sub L bar, which you can do, I can now write down the equation for V sub L bar. That's now that impedance 78 plus J 59 times I sub L bar. Is that okay? Why did I say I sub L? Let me just call that something else. It's the same, it's series, but let me call that I total. And how do I find I total? That's just Ohm's law, isn't it? Except now the impedance is the total impedance seen by this voltage source. So I add up all my real parts, I add up all the imaginary parts, and now that's my total impedance. I now know that I sub t bar, it's in phasor form, is 220 at 0 degrees divided by so there's this V sub S bar over Z total, and these numbers have been calculated to be nice. I now have 80 plus J 60 for my total impedance. And now I have a right triangle with one side being 80 long. The real component of this impedance is 80 long. The imaginary part, or the part that's perpendicular to the real part, is 60 units long, and I now have an idea about how the current is going to change based on the applied voltage. You could now say that, oh, if I now wanted to look at this impedance in terms of a real part and an imaginary part, there's Z sub t, but I could also write that as a magnitude at some angle. And what is Z sub t? That's the hypotenuse of this right triangle. It's actually a 3, 4, 5 triangle, just doubled. But if this side is 6, this side is 8, how long is that hypotenuse? Well, the one side is 60, the other is 80, so it's going to be 100, isn't it? So now we have this is, if you wanted to do it, you could say, well, it's the real part squared plus the imaginary part squared. If you didn't see that, you could do the calculations. That's the magnitude, and now the angle has an inverse tangent of opposite over adjacent. And this now is going to be 100 at this 36.87 degrees. That's now the impedance. Once you have that, you can divide that into 220 at an angle of 0. So what I'm saying is between now and maybe Monday, you need to start getting familiar again with complex manipulation of complex numbers, or working with phasors, so that this just becomes second nature. And drawing these pictures. If it's not making sense, draw a sketch. Oh, what is this complex number? Well, it doesn't make, well, just draw its real part and its imaginary part, and now hopefully you start to see what it looks like in terms of its angle and magnitude. What if I now wanted the power in that circuit? A lot of different suggestions here. Which one is it? It's yours? You're always right? Good. So I'll come to you when I have a question, right?
I'm the interviewer.
You're the interviewer. Oh man, tough crowd here. But we have different ways of talking about power. But you can always say power is VI, right? Well, what is that? Well, P of T is V of T times I of T. And what kind of power is that? That's instantaneous power. You could find I of T. We can find that. We could find V of T. Oh, is this going to be a mess? We have now a cosine, a sinusoid, and another sinusoid product together, but that's our power, and it will be going silly, but we can talk maybe a little bit more comfortably with what it does on average. What's the average power? This is actually the instantaneous power, but we could calculate that. And that's going to be some really fast moving, because now we've now multiplied a cosine 377t, and I is also a cosine 377t. There's maybe a phase shift between those because we have energy storage elements. We have these inductors. We have the amplitude. And now when you take the product of a cosine with another cosine, you start looking at your trig tables, right, or your formulas. But we can simplify that by looking at these in terms of phasors. And we can also say, well, I don't really care how that's working instantaneously. On average, what kind of power am I pulling into my load or into my house? Or now I'm receiving how much power on average from this alternative energy source? What's the average power? So you could find the average. We know what its period is going to be because we'll know what the frequency of that P of T is. We can integrate over one period to get our average. And then we can think about the average, or we may call that, which it is, the real power, and the units of that will be in watts or kilowatts. And that's where we will start this class, is talking about different kinds of power. Not only do we have instantaneous power and average power, but we have other powers to play with. We have reactive power. How much power is associated with these energy storage devices, these inductors and capacitors? Those actually take it and then they give it back. These are ideal devices, so it's kind of weird, but they absorb it and then they give it back. They absorb it and give it back. All the absorbed power is due to the resistive components of these loads. But we'll see that these reactive pieces make it more difficult to push power to different locations. So it would be helpful if everything looked more like resistors. But these industrial facilities have machines in them that might effectively have a lot of inductive parts to them, and they have some big L's, and now that phase shift and the amplitudes are bigger. It's making the power company's job of delivering a certain average power more difficult because you have a complex load that you're applying to the system. And we need to we don't want to keep track of it, but we should, because the power company is going to charge us more if we're having them create more reactive power than what we see in the average power. So we need to keep track of that because it has an economic consequence. And we'll give this different units. Power is always V times I, or volt amperes. That's the VA, but this one's reactive. So we'll have units of VARs. Volt amperes reactive. That's what VARs is. And that means, that's the reactive piece. We add those up, in orthogonal directions. We have average power, the real part. We have the reactive power, which is 90 degrees from that. And we'll get a complex power. If somebody now says, oh, what's the power? Now you have all sorts of ways of answering. You want the complex power, you want the reactive power, you want the average power, or how about the apparent power? Let's write that down. We also have apparent power. The apparent power really is the magnitude of the complex power. This will all, you're going to be aces at this by exam number 1. But this one has units of volt amperes, as does the apparent, because it has a real component and a reactive component. The complex and the apparent is the magnitude of that complex power. This is what we're going to be doing. This is probably new to you. And we'll talk about this relative to single phase. That's chapter 10. And then we'll move into when we want to talk about more substantial delivery of power. Now we want to do it with larger quantities. Maybe it makes economic efficiency sense to start playing with 3 phases of power. And we'll deal with 3-phase power in chapter 11. If you hadn't guessed, now we're working our way through the outline of the course. This is our 30,000 foot thinking of what you're going to see throughout the semester. But you're starting with where you left off 220 with sinusoidal steady state analysis. And we'll immediately start talking about power. That's chapter 10. But you need to be comfortable with sinusoidal steady state. That's now chapter 10 and 11. Well, that's not the rest of the book, is it? And what we want to do now is worry or learn how do we generalize beyond. A lot of time in 220 was DC analysis, wasn't it? You had these constant sources. Then at the end you said, oh, I have sinusoidal sources. What if I have something other than that? How do I analyze it? Do I just leave? Walk off? That could be a solution, but not the most effective for this class. So what we want to do is generalize this sinusoidal steady state. It was kind of fun playing with these complex. Now we don't have to do all this trig. We can just convert it into complex numbers. Can we do something similar and make it even more generalized than just sinusoidal steady state? And I wouldn't ask that if we couldn't. So the answer is yes. That was a coin flip, but the yes part was the answer. Yes or no was the coin flip. But now we want to move beyond 3-phase. We want to generalize from sinusoidal steady state, and that's going to then lead us into Laplace. Now we're going to be getting somewhere. Now we have Laplace transforms, and what's the big deal about that? Well, that now allows us to worry about transient phenomena. In the chapter 9, 10, and 11, we're assuming that the transients have all sort of dissipated, and we're in sinusoidal steady state. We're all shaking at the same frequency. All the transients have disappeared. Now we want to be able to analyze these systems when we might be in a transient condition. So the Laplace transform generalizes the steady state, sinusoidal steady state, allowing us now to actually have transients and steady state. Or somebody might say, well, what's your forced response? Maybe you kick a system and it shakes a while and then it starts stabilizing. You want to know, how did we get to that stable condition and how did we reach and what's happening in the sinusoidal steady state? Laplace allows us to do that. And we can also, with Laplace, account for initial conditions. We can now incorporate initial conditions. And we can deal with all sorts of L's and C's. We can have more than just one or two energy storage devices. Where the energy storage elements are these L's and C's. That now takes us a little bit further. Now we can start talking about systems and finding the transfer functions associated with the system. I was sort of illustrating this. I was walking up and kicking a system. Well, now we model the way this table behaves when it's kicked. And when I say kicked, when you go in and have a circuit and you energize it, that's kicking the system. We may want to know what's the transfer function between the input and where I'm measuring the output. That would be the transfer function of this system, this circuit. And that, because we're dealing with Laplace, it could be more than just electrical circuits. It could be a mechanical system. And we now know how to model it so that we now have its transfer function. You now have this automobile's dynamics described by a transfer function. Well, I know how to analyze it. And I'm an electrical engineer. It's okay. You now know how to deal with these systems because you can understand transfer functions. Or we can now say that if we had, and this now is in the frequency domain, where instead of just omega, we now have an S, which is a complex frequency variable. It can have an omega piece, but it could also have a real piece. So S could be a sigma plus j omega. This is just a complex frequency variable. And it definitely now is generalizing. In the past, in chapter 10, we were only worried when S was equal to j omega. Now it has a real component, a sigma to it. And we need to understand, okay, what's happening when we have an S that's not just j omega, but it's a complex number. That allows us, if somebody said, oh, I have a transfer function and it's now capital H of S, then if they tell you what the input is, you find the input's Laplace transform, that's capital V sub I of S. Now all of this calculus, all this differential equations, we're simplifying it because now we can play in the frequency domain and we simply multiply the transfer function times the input's Laplace transformed expression and we obtain the output signal's Laplace transformed expression. You want its time domain? We run into the time domain. All we do is inverse Laplace transform. And then we have little v sub o of t. But going into the frequency domain allows us to do this analysis a little bit more easily than playing in the time domain where we had to solve all these differential equations, coupled differential equations. Now we have a transfer function, which is some ratio of a numerator polynomial in S and a denominator polynomial in S. V sub I is similarly configured. It's a rational expression. We multiply those together and we inverse Laplace transform and we have the time domain expression. We move back into the time domain. And I'm trying to illustrate this because I want you to get it. We're going to be playing in the time domain and the frequency domain, and you need to be comfortable moving back and forth between those domains. And what you don't want to do is mix them. It's kind of hard to be in the kitchen and the living room at the same time. Oh, this new open floor plan, maybe it's not, but if you had these in separate rooms, now we're in the time domain in the kitchen, and in the frequency domain we're in the living room. We need to play in one room and then say, oh, we need to move. Okay, let's go back into the time domain. You need to inverse Laplace transform. You don't want time domain signals and frequency domain signals playing around together. Where were we? Oh, now you could, instead of drawing these circuits, you could say, oh, there's the transfer function. Now you just have it as a block in a block diagram, and you can say, here's the input, V sub I, and here's the output, V sub O. And now you can think about this in terms of a very general and abstract notion of a block diagram. This is now the middle chapters of the last half of the textbook. This is the Laplace transform material. We can now be saying, well, I actually want to know what this system might do if I walked up to it in the time domain and kicked it. Kicking now is an impulse. If you're in a mechanical class, you might have an impulse hammer. You're hitting your mechanical system with an impulse. You know what an impulse is, right? An impulse waveform. Boom! Right at one point in time, right? That's what we're doing when we're kicking it. But what does that do to the physical system? Boom! It energizes all of these energy storage elements, and then they just behave the way they're going to behave after you remove the impulse. And you're not hitting it, but at time, let's say t equals 0. Somebody might say, well, what's the impulse response? What's this look like as a function of time? You go, oh, I can find little h of t. That's just the inverse Laplace transform of capital H of s. This is now what you would see if you walked up to your circuit and applied an impulse response to it, an impulse waveform, and what you see at the output is its impulse response, the response of that circuit to an impulse waveform. That's what we're meaning by an impulse response. And the impulse response might look like, maybe it looks like this. That's now, let's say, h of t. You go up and kick it, and now that voltage, whoa, and then it just decays exponentially. That's the impulse response of this circuit. And we can start connecting all of these things. Somebody says, well, I really want you to go back to chapter 9 and work some sinusoidal steady state problems. I'm already in chapter 14 with Laplace. You want me to go back? Well, we can connect all of these. We can now find the frequency response of a system by taking this transfer function that we found, h of s, and replacing s with j omega. This now gives us h of j omega, which is, in fact, the frequency response of our system. You've seen this, maybe. Maybe this is generational. Maybe I'm dating myself. How many have graphic equalizers on your stereo? No, you didn't have to laugh that hard. But have you even heard of a... Okay, so Google graphic equalizer. That now tells you how you're shaping your frequency response of your system. You maybe want to emphasize the bass, or maybe you really don't want the bass. You want the vocals, so you accent or elevate the treble area, and maybe you don't want all this high frequency, so you really lower that. You've now talked about a frequency response of your stereo. So this frequency response tells you how your system behaves to certain frequencies. Does it really shake? Does the amplitude get bigger at that frequency? Does it maybe not do much at that frequency? Or at high frequencies, I don't want to move, you're too high. So it doesn't amplify much or scale much at a high frequency. That's the frequency response, and we're going to learn how to sketch that from a transfer function. You're going to now get a picture of that, not with your smartphone. Well, you could probably find an app that will do this, but we're going to be sketching Bode plots or learning how to draw Bode plots. Have you heard of those? No? Yes? Well, you've heard of them now, and you're going to be tested on them in the final. You're going to now be sketching something that looks like h of j omega in dB, and maybe it now looks like this, where this is now frequency. What would you say that shape is if this is the magnitude response of your frequency behavior of some system H? If I said this represents a filter, what's that filter doing? So now we're going small frequencies to high frequencies, left to right. The leftmost side is low frequencies. The rightmost side is high frequencies. What's this magnitude response saying relative to low frequencies and high frequencies? Which one does it favor? Low. So now this is going to pass low frequencies and attenuate high frequencies. This is a low-pass filter shape. We're going to learn how to build low-pass filters, high-pass filters, and band-pass filters, and now you can sketch their Bode plots just knowing how they're described. We also can so this tells you how your system responds for a particular frequency. If I put in this frequency, omega 1, I now know the amplitude that the system is going to use when I put in that frequency at omega 1. If I put in an omega 2 over here, that system's not going to favor omega 2 as much as it favors omega 1 in terms of how big it's going to scale that input waveform at that frequency omega 1 versus the frequency at omega sub 2. That's Bode plots. And you'll learn how to do not only the magnitude, but the phase. And the phase tells you how it's shifted in time for different frequencies. You're going to be sketching two plots. When I say sketch the Bode plot, if I don't say do the magnitude or the phase, oh, I have to do both. You'll do the magnitude plot and the phase plot for the Bode plot. What if somebody says, I'm not just going to put in a sine wave. I want to put in a complicated waveform, V sub I of t. What's the output going to be? Not a problem. I learned it in 320. I'm going to take the impulse response and convolve it with your crazy input, V sub I of t. Done. So you're going to take h of t, the impulse response, together with some generic input waveform that somebody's being smart and saying, well, it's not really a sinusoid. I don't care. Tell me what it is. Here's now a generic input. you're going to combine those in the time domain via convolution. And I know you already love convolution, don't you? Have you heard of it? Never heard of it? Well, you'll know it by the end of this class. This is now our impulse response. And it actually gets kind of fun because we flip and slide waveforms. We get to flip a waveform and slide it through, and we're going to calculate the output. And that's actually what, if I wanted v sub 0 of t, that's h of t convolved, that's a special operator there, convolved with v sub I of t. And that means, and this would be our output response in the time domain. Meaning, suppose that I applied to the system some v sub I of t. And our impulse response for that system was something like that. And now you want to draw on top of v sub I v sub O of t. It's actually going to be something, maybe, depending on this impulse response kind of looks like an impulse waveform if we made this sharper and that was really high, right? That h of t would look like a delta of t, but it doesn't really look quite like an impulse, so that's why this green doesn't quite look like v sub I. The closer h looks to an ideal impulse waveform, the closer the green would look to the blue. Meaning, if h of t was sharper, then this one might look more like that. Is that helping? This is now v sub O of t. And we found that by doing convolution. We'll figure that out. The other thing that we'll play with is what's going on behind the scenes in that graphic equalizer. We're going to learn how to make that happen. In what way? By using filters. And we'll be able to design filters. We'll do different kinds. We'll have passive filters made up of R's, L's, and C's. There's no external supplies, voltage supplies, or power supplies being added, so they're passive. We might actually put some op-amp filters together, and now we have active filters. Well, I'm getting ahead of myself, but I'm looking at the time. Here is a filter. Have you seen that filter before? What kind of a filter is this? This you might be asked on an interview. This you'll just say, oh, that's a low-pass filter. And you'll be able to analyze that with the techniques that we learn in this class. This is now a passive low-pass filter. We'll say, well, I don't really want to work with passive. I actually want a higher order filter. I want my filter to be sharper, meaning a sharper cutoff. Maybe I want active filters. Then we'll put op-amps together. And we'll build higher order filters. Then we'll talk about two-port networks. 2 ports, we have an input port and an output port. And we'll generalize this idea of filters and transfer functions to 2 ports, which you might learn in electronics or in electromagnetics. And then we might get into even more general waveforms that are periodic, and we can talk about Fourier series and Fourier series analysis and how to deal with that. That's where we're headed. I might fill in some of the notes, but I described them verbally. You now know where we're going from chapter 10 all the way to the end of the textbook. I'll see you next week.